module, you will learn about circular motion and banking. Have you ever wondered why a velodrome track is curved? Or, on a rainy day, while driving a car at high speed, what happens if you take a sharp turn on a flat road? You will get the answers to these questions in this module. You have earlier studied the acceleration of a body moving in a circle at uniform speed. Here, Fc, the force directed towards the center of the circular path, is the centripetal force. Centripetal force, Fc, is equal to mv square by r. A simple example of centripetal force is that of a stone tied to a string and rotated in a circle in a horizontal plane. The tension, T, in the string provides the required centripetal force. This tension in the string is due to the pull exerted on the string by the person, which prevents the stone from flying away. Similarly, a car moving along a circular path at uniform speed also requires a centripetal force to keep it moving along the desired circular path. In this module, we will analyze the forces acting on the car during this motion. Let us consider a car moving on a level, curved road. There are three forces acting on the car, namely, weight of the car, mg, normal reaction, N, and frictional force, F. As there is no motion in the vertical direction, the net force in the vertical direction is 0. We can say that normal reaction is equal to the weight of the car, mg. Let us call this equation 1. The static frictional force between the tires and the surface of the road opposes the impending motion of the car in the lateral direction away from the center of the circle. This frictional force, F, is less than or equal to the product of the coefficient of the static friction, mu s, and normal reaction, N. Let us call this equation 2. Substituting equation 1 in equation 2, we get F less than or equal to mu smg. Let us call this equation 3. The centrifugal force, Fc, is equal to the frictional force F. Let this be equation 4. However, Fc is equal to mv square by r. Where m is the mass of the car, v is the velocity of the car, and r is the radius of curvature. Let us call this equation 5. Substituting equations 3 and 5 in equation 4 and simplifying, we get maximum velocity, Vmax, as the whole root of mu srg. That was about a car moving on a level, curved road. Now let us look at a car moving on a banked road. Let us analyze the forces acting on the car one by one. The weight of the car, mg, acts vertically downward. The normal reaction, N, acts upward perpendicular to the road's surface. The impending motion of the car in the lateral direction is away from the center of curvature in the lateral direction. The frictional force, F, acts opposite to this direction, that is, down the lateral slope. We can resolve the normal reaction, N, into its horizontal component, N sin theta. and vertical component n cos theta. Similarly, the frictional force F can be resolved into its horizontal component F cos theta and vertical component F sin theta. We can represent all the components of all the forces at a point C, along with the weight mg as shown. As there is no motion of the car in the vertical direction, the net force acting along y direction is equal to 0, or n cos theta minus mg minus f sin theta is equal to 0. This implies n cos theta is equal to mg plus f sin theta. Let us call this equation 1. We know that frictional force F is the product of mu s and n. Let this be equation 2. Substituting equation 2 in equation 1, we get equation 3 as n cos theta equals mg plus mu s n sin theta. The car experiences acceleration acting towards the center of curvature. This is the centripetal acceleration, and the force required for this acceleration is the centripetal force Fc. Centripetal force Fc is equal to the net force acting along x direction. This gives us equation 4 as n sin theta plus f cos theta equals Fc. Substituting equation 2 in equation 4 and solving, we get equation 5 as n sin theta plus mu s n cos theta equals Fc. But Fc is equal to mv squared divided by r. Substituting this in equation 5, we get equation 6 as shown. From equation 3, n is equal to mg divided by cos theta minus mu s sin theta. Let us call this equation 7. Substituting equation 7 in equation 6 and solving, we get the maximum velocity, Vmax, as shown. Now, dividing all the terms on the right-hand side with cos theta, we get equation 8 as shown. If the frictional force is negligible, the maximum velocity, Vmax, is equal to the whole root of rg tan theta. You have now reached the end of this module on circular motion and banking. In this module, you learnt that when an object is in uniform circular motion, the force directed towards the center is called the centripetal force. An object moving along a circular path at uniform speed also requires a centripetal force to keep it moving along the desired circular path. For an object moving along a level, curved path, the maximum velocity, Vmax, is equal to the whole root of mu srg. For an object moving along a banked path, neglecting friction, the maximum velocity Vmax is equal to the whole root of rg tan theta.